We're your hosts, Madeline Street
and Garrett Cushman. The rabbit and fox populations and their fluctuations on our campus are crazy. The students need to know.
That's right. Now we're going to take it to our predation master, Callie Pierce, to go over our rates.
Thank you, Madeline. Now let's look at the rabbit population. Rabbit population grows at a rate of 5% of their current population each year. But when there are foxes, 0.1% of the product of the rabbit population multiplied by the fox population dies. The fox population, when there are no rabbits around, die at a rate of 3% of their current population each year. But when there are rabbits, they increase at a rate of 0.02% of the product of the rabbit population multiplied by the fox population. So as we can see, the fox population in respect to the rabbit population changes at a rate of 3% of the fox population subtracted from 0.02 of the rabbit population multiplied by the fox population divided by 0.1% of the product of the rabbit population multiplied by the fox population subtracted from 5% of the rabbit population. And this is all assuming that both rabbits and foxes are together in an environment where rabbits can thrive off of unlimited amount of food that is available. Now let's look at a graphical representation. As you can see from the split field, this is how the fox population changes in respect to the rabbit population based on the population sizes at the very beginning for foxes and rabbits. In our case, we have 200 rabbits and 50 foxes. The fox population moves in an elliptical manner around a center of 150 rabbits and 50 foxes. When there are 50 foxes, the number of rabbits starts decreasing because there are too many foxes. But as they start decreasing, the number of foxes also starts decreasing because there is not enough food. Eventually, the number of rabbits starts increasing again because the number of foxes has decreased so dramatically. And eventually, the fox population will start gaining new birth because there is more food to eat. And you are back at 200 rabbits and 50 foxes. It continues in this cyclical manner on and on through time. Now back to you, Garrett.
Thank you, Hallie. We are now going to take a look at some very interesting graphs representing the populations of foxes and rabbits created by Dr. Euler.
So what we want to do is we want to model the behavior of our populations with mathematical equations. So what we do here is we use Euler's method and we found these functions which model the behavior of the population given the initial condition of 200 rabbits and 50 foxes. So as you can see here, the foxes with respect to time is approximately this function, and the rabbits with respect to time is approximately this function. So as you can see, there's sine and cosine. So one's peak roughly correlates with one's trough, which is describes how predator-prey cycles work. And the midpoint for the rabbits is 150, and the midpoints for foxes is 50. So that's our average populations for each. And then these are both with respect to time. So what we can do is we can get rid of time, and now we have a foxes versus rabbits graph. And that will be important for the modeling that we will be talking about now. Alright, so as we talked about earlier, these are the graphs which we showed back there. So what you can see is that the maximum for the foxes graph corresponds to the declining of the rabbit graph, which makes sense because if there's a lot of foxes, then the rabbit population is going to decrease, and so on and so forth. So the peaks correspond to declining on the opposite graph. And then here is foxes versus rabbits. So what we can see here is the same sort of behavior. And if we look at the midpoints for rabbits, which is 150, and the midpoints for foxes, which is 50, we get this center right here.
The models that we have been looking at so far have not accounted for a limited food supply. The equations that you see below do. As you can see in the equation for dr dt, there is a 1,000 minus our term, which shows the carrying capacity. So the maximum that the rabbits can go up to is 1,000 of population, but this does not occur due to the behavior that we saw in the earlier graphs where the rabbits were limited by the foxes. So now that we have this model that accounts for food supply being limited and the foxes versus rabbits, what we can see here is some updated graphs where you can see the graphs for rabbits and foxes versus time both converge to their midpoints, and the same is shown in the ellipse, which represents foxes versus rabbits.
So, I've heard there is a new strain of foxes that can live longer. Can you tell us about that and how it may fix the overpopulation issues in Australia?
Yes, certainly. Unfortunately, Dr. Putin, who ran this next study, was unable to join us. In this study, a population of foxes that can survive for a very long time without food was introduced to a rabbit population. These foxes were able to kill off the rabbit population within just a few short years, as is obvious from the graphs. Dr. Putin's study is still ongoing, meaning we can't yet see the eventual results of the study. However, I think it's pretty clear that without any more food, the fox population will eventually die off, even if it does take quite a while.
Well, hopefully that solution fixed the issue. There's also a study that has found that rabbits have used green hair dye to blend in with the grass.
In the data computed by Dr. Euler, here you can see that there are different rates in which the rabbits and foxes are moving in relation to time. The rabbits are surviving because they can blend in with the grass, and the foxes are dying off because they cannot find the rabbits. The rates of the foxes and rabbits have changed slightly in graphs, but they are still similar.
Thanks for watching.